In this video, we are going to go over the three energy calculations that you have to be able to use. They're right here, and then when to use them is directly below it, and then these are going to be some word problems. The biggest challenge with these types of problems is going to be identifying which formula to use, so I've highlighted some keywords to show you how to do that and make that a little bit easier. And then just keep in mind, you're going to have to show all your work on a separate sheet of paper the exact same way that I'm doing it in order to get credit. So let's start with, we'll do quite a few of these problems. There is a back, but I'm not going to do the back in this video. They're just an extension of the front side. So problem one, it says how many joules of heat are given off when 5 grams of water are cooled from 75 to 25? So I highlighted cooled from 75 to 25 because that is the clue that tells me which formula I need. So just to review the formulas real quick, there's three of them: Q equals MC delta T, Q equals MHF, and Q equals MHV. When we use them, when the temperature is changing for the delta T one, when there's melting or freezing going on for the HF, and when there's boiling or condensing going on for the HV. So basically you have three things. You have one question to ask yourself whenever you do these problems. What's happening to the water? Are they changing the temperature? Are they melting it or freezing it? Or are they boiling or condensing it? And then once you answer that question, you know your formula. And then once you know your formula, which I have written down here for number one, the problem is almost done. The biggest mistake students make is using the wrong formula. So the first one is obviously a MC delta T because they told me cooled from 75 to 25. So I set it up this way. They want to know how many joules, so there's my X, that's Q. They told me the mass was 5 grams, there's my M. They told me it was water, so I look up the C value for water if you don't have it memorized already. It's 4.18. And then the delta T. They went from 75 to 25. I'm just going to subtract and make it a absolute value, so we're always just going to make it positive, and it's 50 degrees. 50 degree change in temperature. So you do your math, and there you go, 1,045 joules. That's the answer to question one. Question two, how many joules of heat does it take to melt 35 grams of ice at 0C? The common mistake here is everyone sees the 0C temperature, and then they automatically think, well, I'm going to go to the temperature change formula because it has a temperature in it. But that is there to throw you off. They said the word melting, so my formula is going to be Q equals MHF. And if you notice, there's no T in that formula. In other words, water melts at 0, it freezes at 0 as well, and that's it. It doesn't melt or freeze at any other temperature under normal circumstances. We'll get into the non-normal way later in the year. So that's why I don't need to worry about the 0C, because it's always going to be 0. They're just including that to try to throw you off. So you write out your formula, Q equals MHF. You plug in what you know. They want joules, that's my Q. They told me the M is 35 grams, and the HF for water is 334. If you don't know it, you look it up on the reference table, front page, table B. And there's your answer. Number three, how many joules of heat does it take to vaporize 70 grams of water at 100 C? Same idea. Vaporization always happens at 100 under normal circumstances, and these are always going to be normal. And so the formula I'm going to use is Q equals MHV because it's vaporization. They then tell me I have 70 grams of water. The HV for water is 2260. I look it up on the reference table if I don't have it memorized. I multiply the two together and I get 158,200 joules. That answers the first part of question 3. Then there's a second part. It says how many kilojoules does it take? Well, then you just use King Henry to convert joules to kilojoules. Remember, if there's no decimal in the number, it's always assumed to be at the end. So then you just move it 1, 2, 3 to the left to get from joules to kilojoules. So 1, 2, 3. So I just move the decimal 1, 2, 3, and it goes between the 8 and the 2. Now, if you included 158.200, that's fine. Numerically, it's the same. It does have a different amount of significant figures, but we're not really worried about them anymore. So that's number 3. So on a test, if this were a test question, which I will pull from this sheet for the tests and quizzes, I would give you a certain amount of points for getting to here, and then another point for going this far. So that way there is partial credit if you forgot a step or did your conversion wrong. Number 4. How much energy is required to raise the temperature of 50 grams of water by 25 degrees? Now, the thing that they're doing to the water is obvious. They're raising the temperature. So my formula is Q equals MC delta T right over here. So I'm going to write that in. And then I just start plugging stuff in. My mass is 50, so that's my M. They want energy. That's the Q. That's where the X will go. They told me it was water, so 4.18 for C. And now the issue is, what did the temperature change by? Well, my delta T in this case was 25. Now this is it's not, I wouldn't call it hard, but it is something you need to pay attention to. So they're telling you that the temperature went up by 25. So what they're giving you is the delta T. So the delta T is directly 25. You didn't have to subtract. Like on problem 1, it said the temperature went from 75 to 25, so I had to subtract those two numbers to get my delta T. But on this one, they're telling you it went up by 25. I don't need the numbers if they tell me the change. In other words, it doesn't matter if the temperature of the water went from 100 to 125 or from 200 to 225. If the delta T is if the change is 25, then that's ultimately all I really need. So that's where the delta T came from. Multiply them together, and there you go, 5,225 joules. We're gonna do 5, 6, 7, and then we'll do like a couple more, and then that's it. So, next page. So number 5, these are two-step problems. So for number 5, it says 1,735 joules of energy is added to 35 grams of water at 30 C. What is the final temperature? So the first question is always, what are they doing? In this case, there's temperature change because they're asking for the final. So that's how I know my formula, MC delta T. My next step is to figure out my, the common question or the common issue is figuring out what the variable is, because you have one temperature number. But if you notice, I just said it, you have one temperature number, you don't have the second one. So you can't tell the change in temperature without having both numbers present. So it turns out the thing you're actually solving for is going to be MC delta T. So let's take a look. They tell you you have 1735 joules, that's my Q. They tell me I have 35 grams, that's my M. They told me it's water, there's my C. And the temperature was 30 and it changes to some other number, so I don't know the change. In other words, I don't know the delta T. In order to get delta T, you either need to know the change or you need to know the two numbers and then you subtract them. I don't have those two, so that's what I want. So I solve for my delta T and I get 11.9 degrees Celsius. That's my delta T. If you rounded it to 12, whatever, it doesn't really matter. So now that's only half the answer. So we know that the temperature change was 11.9. That's not the final temperature. All that means is that the temperature either went up by 11.9 or down by 11.9. In order to figure that next step out, you have to go back into the question and reread it. There is a second way of doing this. It's a little bit more complicated, so I'm not going to teach it. It has to do with temperature final minus temperature initial. We're not going to get into that level of detail here. So I go back to the reading, and they tell me that the water was at 30. They tell me that the energy was added to the water. So if you have water at 30 and you add energy, is it going to go up or down in terms of temperature? The answer is up. We know how much it goes up by. It goes up by delta T. So that means that the final answer is that the water was at 30. I added the energy when it went up by 11.9. So the new temperature would be 41.9 or 42. That part doesn't matter. Rounding's not that important. So that's how you do, that's the easiest way to do these questions. There is a way using delta T where you could do it all in one step, but it is a lot more complicated because you have to worry about delta Q as well, which is why we're not going to really get into it in this video. So number 6, it's the same question, basically. The only difference is now the energy is being removed. So we'll go through number 6 a little bit faster. So it's an MC delta T. You do not know your delta T, you solve for it, you get 14.6. That's my change, not my final answer, but it is halfway there. So if I look at the question, they say the water was at 80. The energy was removed from the water. So if you're removing energy or heat from water at 80, is it going to go up or down? Well, the temperature is going to decrease. So now I know that my final temperature is going to be 65.4 because I was at 80. They removed the water, so it wants to go down by the change. Therefore, the new temperature is 65.4 degrees C, or just 65, rounding doesn't matter. We'll go over 7, because 7 is basically the same problem. Again, I'm just going through all the variations of this type of problem. There's really 4, right? There's either you're giving the starting temperature, and then the temperature is going to go up or down to get the final. Or they can give you the final temperature and ask for you to go backwards based on those same 2 conditions. That's why there's 4 variations to this problem. Other than that, there's no more. So for number 7, it's an MC delta T. They give me 55 grams for my water. They told me it was water, so that gives me my M and my C. They told me 2565 joules, that's my Q. The only thing I don't know is my delta T. I solve for my delta T, and I get 11.2. Now, the key here in this question is that the water was heated to 45 by adding some amount of heat, some joules, right? Heat. When you think of joules, think of heat. What's the initial or the starting temperature? So now think about it. If the room was heated to 45 degrees, was the starting temperature above or below 45? If I said, oh man, I turned the heat up, it's now 45. Well, before I turned the heat up, what was it, above or below 45? Well, it would be below 45. And so therefore, I went backwards. I started here at 45, and I said, okay, that means since they were adding heat to it, and this was the ending temperature, the starting temperature had to be under that amount. That's why I went down, literally. It doesn't really matter how you set this up as long as you understand it. And I'm gonna go down by 11.2 degrees C. I can always fix that later. Okay, so there's my down. So my starting temperature was 33.8. Number 8, it's the exact same problem, except if you notice I changed one word. It was cool to 45 by removing, so it's the inverse of this question. You can figure that out. Let's talk about number 9. So 9 says a 25-gram sample of a substance. Notice they use the word substance. They didn't call it water. So the trick here is that I can't use the numbers for water. So I can't use 4.18, 334, or 2260. None of those numbers apply for this because I don't know if this material is water. It might be, but I haven't figured that out yet. So it absorbs this many joules of energy and melts completely at its melting temperature. What's the heat of fusion for this substance? So my formula, because I know I'm dealing with melting, is Q equals MHF. Even if you didn't know what you were solving for, just plug in everything you know and then figure out the thing that's left. So in other words, I know I have a 25-gram sample, so that's my M. And they told me it has 3,750 joules of energy that gets absorbed. So therefore, that's a Q. So if I think about it, I only have one variable left, and that's the HF variable. Be careful, sometimes people will confuse this and they'll think H and F are two different variables. They are in fact one thing. So I solve for that and I get some number, and I get 150 joules per gram. Now, that's my answer. Let's go over the units because the units can throw people off. Basically, here's how it works. All HF units, all HF numbers for every individual material have the same units. The same goes for C and the same goes for HV. So if I didn't understand or know the units, all I would have to do is go to the 334 number for water, and I'm just going to go to the HF for water, 334, there's the units. So while not every substance has a different number, every HF for every substance has the same units. So therefore, I can just grab the units from the HF number for water and then just write them in. Okay, so there's number 9. The last things I want to go over that actually we're done with the math. The last thing I'm going to go over is going to be 10 and 15. So for 10, it says, what is the minimum number of joules needed to change 40 grams of water to steam? A lot of students have problems with this because they don't know what's going on. Well, what are you doing when you turn water, which is a liquid, right? Maybe I could have inserted the word liquid water, but when we say water, we typically mean a liquid, to steam, which is a gas. So when a liquid turns into a gas, that's boiling. So my formula for that problem is Q equals MHV. And then for number 15, it says how many kilojoules are absorbed when 1.2 kilograms of water are completely vaporized. So my formula is HV again, but the thing you need to worry about this problem is specifically right there. They give you 1.2 kilograms. So before I do this problem, I'm gonna have to convert kilograms to grams. And then when I get my answer, it will be in joules, and then I convert it back to kilojoules. All right, so there is going to be, this is a harder question. It's an easy question, but it's all the conversions that make it harder. The back page is more of the same. So that concludes the explanations on some of the problems on this video. Make sure you show all work to get credit when you eventually hand this in.